For centuries, magnetism and electricity were observed as separate physical properties. You could map the static magnetic waves of a lodestone, and you could feel the shock of an electrical discharge, but the two forces appeared to operate in total isolation. In the early 19th century, Michael Faraday began interrogating this physical boundary from a laboratory in London. Simultaneously, across the Atlantic, physicist Joseph Henry was conducting independent experiments on the same physical questions. Neither scientist had access to modern electronics. Their work relied entirely on raw materials: copper, iron, glass, and rigorous analog observation. By this point, the scientific baseline was established. Researchers knew that running an electrical current through a copper wire creates a magnetic field. Faraday and Henry wanted to reverse engineer that process. They needed to determine if a magnetic field could be used to generate an electrical current. Pinpointing the exact physical conditions required to trigger this conversion would provide the theoretical blueprint for the mechanical generation of electricity. To test if mere proximity to a magnet causes current, we start with what is now known as Experiment 1. This diagram outlines the specific components required: a stationary, multi-turn copper coil connected to a measuring instrument called a galvanometer, and a standard permanent bar magnet. When the magnet sits perfectly still next to the coil, the galvanometer reads absolute zero. There is no electrical activity. The first critical observation occurs when the north pole of the magnet is physically pushed toward the face of the coil. The galvanometer needle deflects immediately. This proves the momentary presence of an electric current running through the wire. But this phenomenon operates under a strict temporal constraint. The current ceases the moment the magnet stops moving. Directionality also follows a predictable rule. Pulling the magnet back away from the coil creates a current flowing in the opposite direction. The speed of the action matters too. Moving the magnet at a higher velocity directly increases the amplitude of the induced current. Finally, the system relies on relativity. Locking the magnet in place and moving the coil toward it yields identical experimental results. Based on this specific set of data, relative physical motion appears to be the absolute prerequisite for generating electricity from magnetism. The next logical step is to isolate the variables. Is this current generation tied specifically to ferromagnetic materials, like a solid bar magnet? This schematic for Experiment 2 details a modified setup that removes the permanent magnet entirely. Instead, a primary coil connected to a battery generates the magnetic field, effectively functioning as an electromagnet. To test this, the powered primary coil is physically translated toward the stationary secondary coil. The secondary coil's galvanometer deflects exactly as it did when the solid bar magnet was used. Reversing the physical motion of the primary coil reverses the direction of the current in the secondary coil. This confirms that the physical nature of the magnetic source is irrelevant. The induced current only reacts to the magnetic field lines themselves. Both of those tests rely on a physical object translating through space. But is mechanical motion actually required to induce a current? Looking at this third experimental design, we lock all components firmly in place along a central axis. The primary circuit on the right is now equipped with a battery and a tapping key, a simple switch, to manually control the current flow. The secondary circuit on the left remains connected to its galvanometer, sitting perfectly motionless next to the primary coil. The instant the tapping key is pressed closed to complete the circuit, the galvanometer shows a sharp momentary deflection. While the key remains held down, allowing current to flow constantly, the galvanometer returns to zero. But the instant the key is released, breaking the circuit, the galvanometer deflects again in the reverse direction. A completely stationary system just generated an electrical current. The earlier assumption that mechanical motion was a requirement for induction no longer holds. If neither the coils nor a physical magnet moved, what physical change actually swept across the secondary coil to trigger that induction? This diagram captures the behavior of the primary coil's magnetic field at the exact moment the switch is closed. As the current builds from zero to its maximum, the primary coil's magnetic field physically expands outward into the surrounding space. As this field grows, the invisible magnetic lines sweep across and penetrate the wires of the stationary secondary coil. Once the current hits its maximum threshold, the magnetic field reaches a static size, halting its outward expansion. Because the field lines are no longer actively sweeping across the coil, the induction ceases. Now observe what happens on the right side of the diagram, the moment the switch is opened and the current drops. Without an active current to sustain it, the magnetic field rapidly collapses inward, shrinking back toward the primary coil. This collapsing boundary sweeps backward across the secondary coil, triggering the reverse deflection in the galvanometer. The expansion and collapse of the magnetic field acts as a functional substitute for the physical motion of a permanent magnet. Reviewing the three scenarios allows us to identify the single common denominator driving electromagnetic induction. We tested a moving bar magnet, a moving primary coil, and a static coil projecting a rapidly expanding field. To unify these observations, look at this 3D model of a single copper ring, focusing on the two-dimensional cross-sectional area inside the loop. This introduces the concept of magnetic flux. Flux represents the total number of magnetic field lines piercing perpendicularly through this specific cross-sectional area. In the first two experiments, physically moving the magnetic source closer forced a denser cluster of field lines through the coil's defined area. In the third experiment, toggling the switch created an expanding magnetic field that similarly changed the number of field lines through that area, requiring no mechanical motion. This also explains why the steady state fails. When the flux is high but completely static, meaning no new field lines are moving in or out of the area, zero current is generated. The absolute magnitude of the magnetic field does not matter. The physical motion of the components does not matter. This leads to the formal definition of Faraday's law of induction. An electromotive force is induced in a closed circuit if, and only if, the magnetic flux linking that circuit changes over time.